Today, I am excited to talk about a topic in modern cosmology, the Hubble constant tension. In 1929, an astronomer Hubble published a linear relation between the apparent distance to galaxies and the velocity. This simple plot provides the evidence that our universe is in a state of expansion. The Hubble constant, denoted as H0, is a key parameter that describes the rate at which our universe is expanding. It is measured in kilometers per second per MPC. Simply put, it tells us how fast galaxies are moving away from us as the universe expands. However, recent measurements of the Hubble constant have revealed a significant tension between different methods of measurement, which has led to profound questions about our understanding of the universe. For measuring the Hubble constant, there are two primary methods used to measure the Hubble constant. First, cosmic microwave background measurements. The first, measure, the first method involves observing the CMB radiation, which is the after law of the Big Bang, through the derivation of Friedman equation. We can obtain the expression for the Hubble constant. Due to time limits, I will not present the detailed process here. By analyzing this radiation, scientists can infer the Hubble constant using the standard cosmological model known as lambda cold dark matter model. Using dark matter density, beyond density, and matter density, the Planck satellite, which provided detailed measurements of the CMB, estimates the Hubble constant to be 67.4 kilometers per second per MPC. Second method, local distance measurements. The second method focuses on measuring distance to nearby astronomical objects, such as supernovae and the Cepheid variable stars. We can use the definition of luminosity to determine distance between star to us. D is distance, L is the absolute luminosity, B is the apparent brightness. The stars serve as standard candles for measuring cosmic distance. There is a relationship between the absolute luminosity and the period of Cepheid variable stars. We can obtain its luminosity through period filtering. After measuring the apparent brightness, the distance can be determined. A notable study by Rice et al. In 2016, they used three methods to measure the distance: Milky Way parallax, LMC detach the ellipse binaries, use the photometry of Cepheid in LMC and estimate of the distance to this galaxy based on detached ellipse binaries, and DEBS in M31 make use of a sample of 375 Cepheid in M31 in order to help characterize the Cepheid PLA period and luminosity relations. This systematically address the errors in the results obtained from these different methods, ultimately reporting a Hubble constant of about 73 kilometer per second per MPC, indicating a faster rate of expansion in the local universe. These two methods yield significantly different views for the Hubble constant, which brings us the concept of Hubble constant tension. For impact of Hubble constant tension, the the discrepancy between these measurements is not just a minor detail. It raises important question about our understanding of universe. The difference of about 5 kilometers per second per MPC is statistically significant and suggests that there may be something fundamentally wrong with our current cosmological models. This tension could be implied several properties. First, nature of data energy. The accelerated expansion of the universe is attributed to data energy, but the differing reviews of H0 could indicate that our understanding of data energy is incomplete. Another is new physics. The tension might point to the existence of new physics beyond the standard model of cosmology. This could include modifications to gravity or the presence of unknown form of matter, and systematic errors also may be a possible reason. For possible solutions, a famous possibility is a PEDE model, in which a redshift-dependent DE component emerges at late times. The fluid described by equation has the fundamental equation of state that approach the cosmological constant view equal minus one as time processed. Use the new model. We can get H0 is 72.16 using Planck 2018 data. Unif Unified data fluid model are cosmological scenarios where the dm and de behave as single fluid. This single fluid behave as dm in the early evolution of the universe and as de at late time. This model indicates H0 is 71 using Planck 2015 data. The above two methods are just two of the possible results that are relatively close to the mission shared distance view. Due to time constraints, more methods can be found in the reference. Concluding, in concluding, the Hubble constant tension is a fascinating and critical issue in cosmology. It not only changes our current understanding of the universe, but also opens the door to new discoveries and theories. As we continue to explore the cosmos, it is essential to remain open to new ideas and evidence that may reshape our understanding of the universe we inhabit. Thank you for your listening.